Today we shall solve the problems what I had given in the previous session. The first problem was C2H5 to this BH3 THF OH minus H2O2 and H2O. So for this we need to write down the answer along with the stereochemistry. So when BH3 is there, both hydrogen and OH groups will add from the same side. And next one is, as we write down the stereochemistry, just wait. Let us take the C2H5 is below the ring, so that the hydrogen and OH groups comes at the top. This is the answer for this question. And the second question is CH3 BD3 deuterated diborane OH minus H2O2. So the answer for this one is, concept was discussed yesterday. You can go through that concept. CH3 as it is we are writing. Now here OH group and deuterium both will be added from the same side. And one more thing is OH group will go to the less substituted carbon. So imagine the CH3 is top of the plane, and here let us take the deuterium, and here let us take the OH. This is the CH3 one. And the C is pH, CH double bond CH2. So here HgOAc taken twice. Mercuric acetate, you can observe that they had given the methyl alcohol, not the water. NaBH4 OH minus. So let's write down the product here. pH, CHOCH3 and CH3 without rearrangement gives the Markovnikov's product. If H2SO4 is used, it gives the Markovnikov's product with rearrangement. And the last question what I had given yesterday in previous session was this one. This is again with mercuric acetate H2O now, again NaBH4 and OH minus. So if anybody missed these concepts and how to write down these products, you just go through the previous video which is posted in our classroom point, so that you can understand the entire concept and comment all these questions again. So this is the one. So these are the answers for the questions given in the previous video. So today's session is about the addition of nitrosyl chloride. It is not there in the NEET. You can skip this question or concept if you want. It is called as the Tilden's reagent. So first of all, before knowing that, what is nitrosyl chloride? NOCl is called as the nitrosyl chloride, and let us try to see the structure of this NOCl N double bond O like this. Here nitrogen carries positive charge and the chlorine carries the negative charge. So that whenever nitrosyl chloride is added to the double bonded carbon, so according to the Markovnikov's part, the positive part of the reagent will be added to the double bonded carbon with more number of hydrogens, and the negative part goes to the double bonded carbon with less number of hydrogens. I'll take one example directly so that you can understand the concept. Double bond CH2 propene. Take the NOCl. Then you can easily expect the product, that is CH3, CHCl and CH2NO. The important thing is, whenever NO part is added to a particular carbon where hydrogen atoms are there, immediately this type of the molecules undergo rearrangement and give the more stable product, that is hydroxylamine. It gives chlorine, so that it forms, this hydrogen will be undergoing tautomerism, ketonal tautomerism, so that it gives the OH here double bond. This is called the hydroxylamine. So if hydrogen is not there, then no rearrangement takes place. That you should remember that. Now let us see the another type of the reactions, that is important one, but very easy, and hope this reaction is not there in the NEET also. Very easy reaction, Diels-Alder reaction. Very easy reaction, easy to understand this reaction also. Diels-Alder reaction. So in this Diels-Alder reaction, it is a type of the addition reaction where conjugated diene, it is also conjugated diene, is added with some alkene and gives cycloalkene as the product. And here the alkene that we are adding here is called as the dienophile. We are calling this one as a dienophile because it likes the diene, so that it is called as the dienophile. And most of these times we take the 1,3-butadiene or generally conjugated dienes. So whenever conjugated dienes are added to the alkene, they give the cycloalkene as the product. Let us see some of the examples. This is a simple Diels-Alder reaction. I will take examples of this reaction. First one is, we just take CH2 double bond, CH single bond, CH double bond, CH2. This is called the 1,3-butadiene. You just see only this reaction, and rest of the reactions you can easily understand. And diene, CH2 double bond CH2. Okay. And here you need to do just only heat it. So the reaction is a thermochemical reaction. This reaction takes place only in the case of the heat. I'll write down the characteristics of this Diels-Alder reaction later. Then how the rearrangement takes place means this pi bond shifts here and comes between these two carbon atoms, so that this pi bond will shift over here and this pi bond will come over here and forms a bond between these two carbon atoms. So overall, I'll write down the skeletal structure. See, this is the CH2 which I am writing. It is connected to a CH. This CH is connected to another CH. This CH is connected to another CH2. And later here two CH2 parts are there. Now one of the bond is shifted between these two carbon atoms. So just make the bond here. And another bond is formed here, so that you get the bond here. And here by the shifting of this bond, here we are getting one double bond. So this molecule will get, this is nothing but the cyclohexene, like this. Okay. And what are the important things to be remembered in this reaction is, whenever this particular diene is more reactive, when it is having electron releasing groups. and a dienophile. This is we call dienophile now. So dienophile means the one that likes the diene is called as dienophile. Why it is liking the dienophile? Because of the having electrons. So this dienophile always likes the presence of the pi electrons over in the diene. So that if this particular diene want to like this diene, if this dienophile would like to attract this diene, then this must have the less number of electrons. If it is have the less number of electrons, then obviously it will attract the diene. So that this dienophile is more reactive when it is having electron withdrawing groups. So electron releasing groups on diene, electron withdrawing groups on dienophile makes this all reaction very easy, or to get the product very easy. Let us see some of these reactions. Later we write down the characteristics of the reaction. So I'll take this is the diene. Everybody has to remember this one. Now this is alkene. To this you add some CHO, that is called as the electron withdrawing group, and heat it. So you will get the product like this. So here double bond comes. Second one is plus OCH3. This is also electron withdrawing group completely. And here electron releasing groups are there. So when you compare these two reactions, this is more reactive. Why? Because diene is having electron releasing groups and dienophile is having electron withdrawing group. Here dienophile is having electron withdrawing group, but diene is not having the electron releasing groups. So that the molecule what you are going to get here is this is the molecule. So third one, let's take one more reaction. Heat it. This is also more reactive because the electron withdrawing group is so strong than this one. So the molecule what we are going to get here is this is the molecule. Now let us see some of the features of this particular reaction. So main features I'll write down here. Main features of the reaction. So the first one is they are initiated by heat. The reaction is completely initiated by heat. So we say that this reaction is a thermal reaction. Okay, so I'll write down here. This is a thermal reaction. Second one is they form a new 6-membered ring always. And third feature is there are actually 3 pi bonds, 1, 2, 3. So 3 pi bonds are broken and 1 pi bond and 2 new sigma bonds are formed. So that 3 pi bonds breaks and 2 new carbon-carbon sigma bonds and 1 new carbon-carbon pi bond is formed. The fourth one is the reaction is concerted. The reaction is concerted reaction. So what does it mean by the concerted reaction? Concerted reaction means the stereochemistry of the reactants will be maintained. Just only rearrangement takes place like this, but no stereochemistry or no position of the atoms will be changed. The position of the atoms as well as the stereochemistry of the groups remains as it is. So such type of the reactions are called the concerted reactions. Okay. So I'll take some more examples for this Diels-Alder reaction. This is very simple and easy reaction. Let us see some more examples of this Diels-Alder reaction. Just heat it. So it becomes easy for you also to write down the product by seeing this. This is diene here. This is dienophile. So here this bond shifts and attacks over to this carbon atom, and this pi bond will shift over here, and this pi bond will form a bond between this particular position and this particular position. So this position remains as it is. That I'll write down. Just you see how I'm going to write down the product. So first of all, basic compound I'm writing. So this basic 5-member ring, this one is the basic 5-member ring. In this here pi bond comes, and the new connections are this one. So these two are new connections. Here cyanide comes. Okay, and third one, an important thing what I am going to inform you here is, say I am taking a diene like this and take the COOH. Whether this reaction happens or not, this reaction will not happen. Then you may ask the question, the reason why. So one particular point I want to discuss here is, whatever the diene we are using, this must be cis diene. Here it is a trans one. So once a trans diene is there, it will not participate in the reaction because the rearrangement of the bonds will not be possible with the trans dienes. So it is completely unreactive towards the Diels-Alder reaction. So only cis dienes results the products. Means cis dienes both double bonds must be on the same side. If any trans is there, then that will not be more reactive. Okay. So now let's take some more examples with, along with the stereochemistry, so that you can understand. Just see here. And heat it. Stereochemistry will never get changed. So here this is cis, this is also cis. Both must be cis. If anyone is trans, always the diene must be cis always. The dienophile may be cis or trans. If both are cis, we get only one product. If both are trans, we get two products. I'll write down that also here. I'll write a note point and later I'll give an example. Cis diene plus cis dienophile on heating gives only one product. And here cis diene plus trans dienophile, we get two products. These are enantiomers. And if you take trans diene and cis dienophile, heat it, no product. Because the diene must be cis1, the dienophile may be cis or trans. If it is a cis, only one product. If it is a trans, two products we get. Let us see that example also. So I will take one diene, this is cis diene, plus let us take the trans dienophile COOH and COOH. So as I said earlier, both will maintain their stereochemistry. Stereochemistry of this reaction will never get changed, hence this reaction is called a concerted reaction. So we need to maintain the stereochemistry of both of these COH groups, means both must be in the opposite direction. But in the open chain compound, we can easily show the position of COH group is in the opposite direction by writing like this. But when it comes to the cyclic molecule, because it is going to be formed a cyclic molecule. So in the case of the cyclic molecules, we cannot put like this, but we can show with a wedge and dash formula showing that one is above, one is below. Enantiomers. Okay. So now let's try to solve some questions. So I'll give the question. Draw the products of each Diels-Solder reaction and indicate stereochemistry. So that I will give some product reactions. Just write down. The first one is diene heated. Though we have written, just I am asking you write down their stereochemistry if possible. So two molecules I am taking diene. This is dienophile and heated. And C and heated, and D CH2 and CH2. Heated. And the last compound is concentrated H2SO4. I request you please solve this one. Now, I am going to write down one important thing here is, I said trans dienes generally do not participate in the reaction. I will correct it here, one small important thing, that trans dienes, that is cyclic trans dienes, no product. But normal open chain trans dienes gives the product. Because when open chain trans dienes, there is a chance for the rotation around the double bond. So they give cis dienophile, heat it, and you will get the one product. Because here I had given one example, maybe somewhere. Yeah, this is cyclic one. Cyclic rotation is not possible, but open chain compounds rotation is possible. So I'll write down the product for these molecules. This is the product, and here two dienes are used, and dienophile is also having the two double bonds. So that what happens here is, first this particular double bond participate in the Diels-Salt reaction with one diene and forming one cyclic ring this side. The other side, one more molecule comes, and this side also same reaction happens, and it gives the molecule like this. And in this case, it can easily be predicted. And this is the trans one, but open chain, so that possibility is there. And the last molecule to be discussed is H2SO4 gives H plus ion. H plus ion preferentially attacks one of these double bonded carbon, so that makes this one as CH2 and CH3 CH2 plus. So this CH2 plus attacks over another particular double bonded carbon, so that shifting of the bonds takes place like this. So the molecule we get here is what we expect: CH2 CH3, okay, and here hydrogen 1 2 3 4, okay, no hydrogen. Here positive charge will be there, tertiary carbocation. So hydrogen from here shift this side and gives a molecule of double bond and CH2 CH3. This is one possibility. The other possibility is if H plus ion attacks over this particular double bond, then we get the positive charge here, okay, and this positive charge if attacks over the CH2 double bond CH2 like this, then we get the molecule CH2 CH2, because these electrons will shift over here, and here it forms the positive charge, and this is a primary carbocation. So what happens? Hydride shift takes place. 1 2 hydride shift, hydrogen shifts over there, so that we get the plus. This is secondary carbocation, which is still unstable, so that methyl group will shift over there. 1 3 methyl shift, so that we get the tertiary carbocation. Now hydrogen will be eliminated and giving the molecule like this, and this is the major product. So you need to see both the products, which are all possible products, but most of the time these reactions we cannot expect, but you better remember the reaction even like this also. Now we are going to discuss the another important reaction, that is ozonolysis of alkenes. Very important reaction, easy and important. So here ozonolysis, just what does it mean by ozonolysis? Means treatment of alkene. Even alkynes also reacts, but we are discussing about the alkenes chapter, so that I am taking on alkene. Treatment of alkene with ozone is called ozonolysis. But this ozonolysis is of two types based on the type of reagents we are going to use. So it is of two types, that is reductive ozonolysis and oxidative ozonolysis. So in reductive ozonolysis, we use generally zinc H2O combination, or we can use the dimethyl sulfide as the reducing agents. In oxidative ozonolysis, we use H2O2 or Ag2O as oxidizing agents. Then what is the difference between these two reactions is, when you use the reductive ozonolysis, it gives only carbonyl compounds as the products. Carbonyl compounds are the final products. In oxidative ozonolysis, we get three types of the products, that is ketones plus carboxylic acids plus carbon dioxide. And in the case of the reductive ozonolysis, we get the ketone along with that aldehyde based on the type of the molecules. So carbonyl compounds means ketones and aldehydes are possible. But in oxidative ozonolysis, aldehyde will not be formed. Ketone will be formed. The reason is, the moment aldehyde is formed, it will be oxidized to the carboxylic acid. So we get the ketone molecules and the carboxylic acid, and from where we are getting CO2 means, if any CH2 is like this, if any group is like this will be converted to the formic acid. That formic acid finally will be oxidized to the carbon dioxide. So that is called the oxidative ozonolysis. I'll take this reaction and I'll let you know how to write down the products in the ozonolysis reaction. Very easy reaction this is. And I'll mention the advantage of this reaction also, so that note down the point. This reaction helps us to identify both position and the presence of double bond. So where the double bond is there, and whether double bond is there or not, or where it is double bond, both can be identified by using this reaction. But in earlier one reaction we discussed, that is bromination, that helps us to identify only the presence but not the position of the double bonds. So I'll take some examples here. So first of all, in ozonolysis, if you take any alkene molecule, that alkene molecule combines with the ozone and forms ozonide. Ozonide in the sense, just break this bond, put one oxygen here, two oxygens down. So we'll get the CH2, oxygen, CH2, because ozone means 3 oxygen. So that like this, and one oxygen here, one oxygen here. This is called the ozonide. So ozonide is the intermediate in the ozonolysis. So when it is subjected with the zinc and H2O, it breaks the bond like this. So every time I don't discuss again and again, just remember like this. So the CH2 combines with oxygen and forms a CH2O, and the CH2 combines with oxygen and forms the CH2O. CH2 is nothing but the HCHO and HCHO, which is called the formaldehyde. So instead of writing this much things, people used to discuss that, add one oxygen here, break this bond, so that you get the CH2O and CH2O. And if you want to get the, sometimes what they say, they give the products like this, and they ask the from what type of alkene these two products are formed. In such cases, you just remove these two oxygens and add these two parts by double bond, and you will get this with respect to alkene. So we shall see some of the examples. So in that first example is, imagine there is a alkene like this plus ozone. Okay, so it forms ozonide. Oxygen, carbon, the oxygen like this, and here hydrogen, here R dash. And this ozonide can be subjected in two ways, that is zinc water, and remember, or dimethyl sulfide also. This is very important because people forget about dimethyl sulfide. So you can use H2O2 or Ag2O. So you know that this is the reductive process. This is oxidative process, oxidation. So in the reductive ozonolysis, you just break this bond and put oxygen here, so that you will get the R C double bond O R plus here R dash C double bond O H. So that R dash C double bond O H. This is ketone, this is aldehyde. So carbonyl compounds are formed with reductive ozonolysis. But in oxidative ozonolysis is not like this. Ketones forms as it is. Ketone is formed and this aldehyde also will be formed, but aldehyde once it is formed it will be converted to the carboxylic acid. It means if any hydrogen is there, that part will be converted to the immediately carboxylic acid, like this. So this is the main difference in the reductive ozonolysis as well as in the oxidative ozonolysis. So let's try to write down some of the products here. So example reactions, maybe second reaction. Now let's see. Both reductive and oxidative ozonolysis, we need to write down the products. CH3, CH2, CH double bond, C, CH3, CH3, ozone. I am not writing the ozonide now. You must understand the ozonide is there. Zinc H2O and this is H2O2. So you should not get confused of what, because ozone is there every time. You don't write down the aldehydes and ketones as the products. You must see that reagent they are using after the ozone reaction. So when zinc H2 is just break the bond, put oxygens both the side. So you'll get the CH3, CH2, CHO plus here C double bond O, CH3 and CH3. These are the products. But when H2O2 is there, then here hydrogen is there, no? So if any double bonded carbon is having at least one hydrogen, that part will be converted to the carboxylic acid. The other part will not be converted to carboxylic acid. Or else if you still get confused of that, immediately write down first product CH3, CH2, CHO plus double bond CH3, CH3 like this, and this aldehyde part you just convert to the carboxylic part. Why? Because aldehyde molecule will be oxidized to the carboxylic acid in the presence of the either H2O2 or H2O. This video will be available. You don't get confused. If you want, you can check it once again whenever doubt arises. So now I am going to give one more product. Ozone. So ozone here zinc H2 as it is used, or else dimethyl sulfide. Okay, no problem. Here you use it Ag2O. So when zinc H2O or dimethyl sulfide is there, just break the bond, add oxygens both the side. This is CH2, again CH3, CH4. Both are aldehydes. And this one is here hydrogen atoms are there, not to the double bonded carbon atom. So both will be converted to their respective carboxylic acids. Fourth one. Let us see one more reaction here. Double bond CH2. Now you can see the difference in the reactions. Ozone we used here Me2S and take the H2O2. So whenever this particular part is there, just break the bond, add oxygens on the both the sides cells at CH3 CHO plus CH2O. But whenever H2O2 is there, hydrogens are there, so that this will be converted to the carboxylic acid CH3 COOH, and here complete CH2O will be converted to the carbon dioxide. If one hydrogen is there, COOH. If two hydrogens are there, directly carbon dioxide only. I'll write down one more product, one more reaction. Just see the reaction CH3 C CH3 double bond, 1 minute, CH3, CH2, C, H double bond, CH2. So I am giving all here only in this particular example only. Ozone, dimethyl sulfide and H2O2. So here break the bond here. So initially you will get the CH3, C double bond O, CH3 plus here also both the side is CH2. Anyhow we are using dimethyl sulfide, so break the bonds and put the oxygens there. This becomes CHO here and that becomes CH2O. And whenever H2O2 is used, then we have to guess the products. Here no hydrogen is there, so this part will be ketone. Plus here also hydrogen is there, is not there, so that this part is also ketone. CH2. But here CH hydrogen is there, so this will become carboxylic acid. And this becomes carbon dioxide. So if anybody asks you that in a particular reaction, ozonolysis, oxidative ozonolysis reaction, one molecule, an alkene is giving ketone, ketocarboxylic acid and carbon dioxide, then write down the IUPAC name of the alkene. Then in such cases, whenever the ketones are there, so that parts must and should be connected by each other. Why? Because no carbon dioxide is formed, means there is no CH part. And here COH is there, here CO2 is there, means here CH is there, here double hydrogen atoms are there on the carbon, so that you can connect. Possibilities are there, but they will give the another clue. With the help of only this clue, you may not be able to find it. For example, I will write down the one question here. An alkene in oxidative ozonolysis gives acetone and 3-oxo butanoic acid and carbon dioxide. Write the IUPAC name of alkene. So here we get one or two products. We need some more information, but with the help of this, let's try to see how to develop the alkene molecule. First of all, they said acetone. So write down the acetone molecule. CH3, C double bond O, CH3 is an acetone. Plus, next one is CH3, C double bond O, CH2, COOH. Plus, next one is carbon dioxide. So the chances of forming this particular molecule is like this. You can connect these two. First chance I am explaining. Connect these two double bonds so that you will get the CH3, C, CH3, double bond C, CH3, CH2. Next, connect these two so that here carbon dioxide, carboxylic acid means 1 CH is there. Carbon dioxide means 2 hydrogens are. This is one chance. And the second molecule will be, you can connect this particular COOH here. Got it? So that you get the molecule even like this also. Double bond CH, CH2, C, CH3 and this CO2 you can write like this CH2. So 2 alkenes will get. That's why I said we need some more information. These are the possible alkenes. So possible alkenes are like this. So this CO2, CH2 part always at the terminal position, otherwise you don't get the CO2. Remaining combinations you can change like this. So in this way we can get the products. Let's write down another some more examples of this particular ozonolysis reactions. Ozone, zinc and H2O. So H2O2. Zinc and H2O means you no need to be scared of this. Simply write down. Break this double bond, put the oxygen. Break this double bond, put the oxygen. This is hydrogen. Because here hydrogen is there. H2O2 means this is keto part, this is carboxylic part. So number of carbon atoms will not get changed. You must be careful while writing the molecule. So I'll give one more molecule. Ozone and H2O2. Okay. Generally, when H2O2 is used, we expect that these molecules will get disconnected, but benzene needs prolonged oxidation. So benzene will be oxidized only under the prolonged oxidation, otherwise it will not get oxidized. Anyhow, let us see the normal products here. Benzene, COOH plus this also becomes the COOH. Later C2H5 is there. This is the one chance. The other one is if the same compound is subjected for the prolonged oxidation, then break all these bonds. So this becomes COOH, 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 COOH. Here COOH, this is CO. So this particular area, because benzene means hydrogen is there, hydrogen, hydrogen, hydrogen. So hydrogen with a double bond, this becomes COOH. Hydrogen with a double bond, this becomes COOH. These two are connected by single bond, so we have it. Another one COOH, COOH connected by single bond. So that two molecules we are getting. And here we get the COOH. Next one is here CO. This is keto part. Next one is this is COOH. And this is as it is C2H5 COOH. This is the original product. So generally they mention it whether it is participating in the prolonged oxidation or just only normal oxidation. Normal oxidation means generally the outside double bond will be broken because benzene is stable. If it is a prolonged oxidation, means even after the breakage of this bond, if you keep on subjecting this benzene molecule for the ozonolysis reaction, this will be the product. Because I'll write down the reductive ozonolysis product of the benzene itself, then you will understand. See, you take the benzene. Benzene means these are all hydrogens, C6H6. Plus, just subject it with the ozone in the presence of the reductive ozonolysis, that is MEP, dimethyl sulfide. So high temperature and pressure conditions. How many ozones you need? For every double bond, you need one ozone. So here how many double bonds are there? 1, 2, 3. So 3 ozones, you use it. And how to break the bond? Since it's reductive ozonolysis, break this bond, put oxygen here, here. Break this bond, put oxygen here, here. Break this bond, put oxygen here and here. So the molecule what we are going to get is, this one is carbon, hydrogen, oxygen. So CHO. Single bond, carbon, oxygen, hydrogen, CHO. So CHO, CHO. Here also CHO, CHO. Here also CHO, CHO. So we'll get the three molecules of CHO, CHO, which is called as glyoxal. And they asked even question once in examination that What is the intermediate product when benzene is subject to the ozonolysis? Triozonide means we have to break this bond now. So just see, I am not breaking the single bonds. Just break the double bond and put one oxygen here, two oxygens outside. Connect these bonds. And put one oxygen inside and two are outside. And put one oxygen inside, two are outside, and connect these bonds, these oxygen atoms. Okay, then Me2S reduct to ozonolysis. Then how to break the bonds? It's simple. As simple as we have written this particular molecule. Just break the bonds like this. Okay, this is another one. This is another one. Then you will get the idea that this is CHO, CHO. This is CHO, CHO. This is CHO, CHO. Again you are getting the three molecules of plants. This is called as, this intermediate product is called as benzene triozonide because three ozonide parts are there. Hence it is called the benzene triozonide. This is the intermediate product in the ozonolysis of the benzene. So I'll give one more example. Just write down the product for this. I'm giving just simple examples here. Write down the products and tell me. Salt. So we shall see the products here. Zinc H2O. The product is CH3, CH2 hydrogen is there, and zinc H2O means just we put the oxygen from the both the sides CH2O, and this is CH2O. H2O2 means you have to see whether hydrogens are there on the double bonded carbon or not. If hydrogens are there, it will convert to the carboxylic acid part, and if two hydrogens are there, it becomes the carbon dioxide. And anyhow here you can directly get the product C double bond O CH3 plus CO2. So here ketone cannot be oxidized by just hydrogen peroxide. It needs strong oxidizing agents.